we are going to start sort of a focus on Bayesian networks. Now, in terms of the big picture, where are we? We have been trying to do some various knowledge representation languages. And the general idea of knowledge representation has been, how do I explain the problem or the world dynamics or the way the world works in general to the machine, right? And we have talked about language of logic, and then we at some point said language of logic is good but not sufficient, which is what led us from the traditional AI, which was very logic driven, to very modern AI, which is highly probability driven. So, what was that change? We have alluded to it, but today we are going to discuss that first, and then we will say, like we have the language of logic in the world of deterministic environments, we will have the language of Bayesian networks in the world of probabilistic environments. Okay. So, this is going to be our running example, and this is a very famous burglars and earthquakes example. Now, in this example, we say that you are done with the AI class. There will come a time when that will happen. I know at this point it looks a really long race, but there will come a time when you will be done with the AI class and you will be like, yes, I am done, we can have a party, right. Not that I am stopping you from having those right now, but I know that because you have assignments and so on and so forth, it is very hard for you, right. So, I understand. Now, suppose you are Julia Pearl, he was doing his AI class and he finished his AI class, he went to the party, and then suddenly his neighbor John calls him to say, oh, his alarm has gone off at the home. Okay. But his neighbor Mary does not do that. Now, you know that sometimes the alarm can be set off by minor earthquakes. There is a small earthquake and the alarm starts beeping, there is no burglary. The question you want to answer is your home being burglarized? Should you leave the very important done with the AI class party and go back and check, what all has been stolen, or should you just continue? I remember a very distinct example where my uncle had gone off on a trip with family, and suddenly he gets a call from the policeman saying, your house has been burglarized. We are standing in front of your house 24/7 to make sure the burglars don't take anything more. Please come back soon. It was like, if they are standing there 24/7 and the burglars have taken what they have to take, let us finish my trip and then come back home, right. So, that was the other way of looking at it. So, Yudia can say, my things have already been stolen, let me at least enjoy the party, right. That is the other way of saying it. But for now, the question is not what he should do, the question is the house being burglarized? Has the house been burglarized? And notice that at some point, you have to realize that we cannot answer this question deterministically. Are you sure that the house has been burglarized? Are you sure that the house has not been burglarized? You are not sure, right. You cannot make a deterministic statement about it. And you have to realize that there are many things that are in play here. A burglar can set off the alarm, the earthquake can also set off the alarm, the alarm can cause Mary to call, and alarm can cause John to call, right. Now, suppose we want to model this as logic, right. Let us think about why we cannot do it. Although I think it should be obvious to many of you, let us just make sure that we think about it. So, of course, Yudia lives in Los Angeles, it is a high crime area, and he has installed this burglar alarm, and he has asked his neighbors John and Mary to call him whenever they hear the alarm, right. So, this is where he can come home if there is burglary, right. Los Angeles is also on the west coast, it is earthquake prone, so sometimes minor earthquakes cause the alarm. Now, if you were using the world of logic to represent this, you would say burglary implies alarm, you would say earthquake implies alarm, you would say alarm implies John going to call, alarm implies Mary is going to call. This is sort of what logic will allow you to do. It will also allow you to ask the question, if there is burglary, will Mary call? You can ask the question that I have this KB of 4 implications and burglary has happened, there is a mistake here, B has happened, now will Mary call? And the answer may be yes, right. And you can alternatively ask the question, if Mary didn't call, is it possible that burglary occurred? And then you can also answer the question, no, it is not possible that burglary. By the way, it does not even represent the possibility that John calls and Mary doesn't call. To a logical world, this logical way of looking at things, this world is just impossible, right? Do you see that? Because earthquake happened, then alarm will go off, alarm happened, then John will call and Mary will call. Maybe you can say that if alarm hasn't gone off, John can still call, so that's possibility exists, maybe the possibility exists, that's fine. But really what is going on in the real world, right, is something like this. He lives in the real world, not in this fictitious world, where burglars have the ability to disable alarms. You know, earthquakes may be too slight to cause alarm. Sometimes there is an earthquake, there may be no alarm. Even in Los Angeles, burglaries are more common than earthquakes. But notice that we have no way of explaining this information to the logical system. John and Mary actually have lives. They are not just sitting there waiting for them to listen to the alarm and give Julia Pearl a call. That's just not going to happen. So, they have lives, right. Sometimes they may be doing things and may not hear that the alarm has gone off, right. Of course, between John and Mary, Mary is more sincere, John is less, right. Sometimes, you know, John gets drunk and, you know, doesn't call. Recently, John and Julia has also had a tiff. So, it is possible that he heard, but he said, I am not going to call, let his house be burglarized. You know, anything can happen. And now, the question is, John has called, if Mary also calls, does it make it more likely that burglary has happened? You should ask that question. This is the kind of question that logic has absolutely no way of thinking about, because it has no way of asking the question likelihood, whereas probabilistic models do. So, how do we handle the real Pearl? Now, there is also the possibility that you may hear on TV that there was an earthquake. Now, you ask the question, is burglary more or less likely now? Right. So, how do we handle the real Julia Pearl? How do we handle the real burglars and earthquake example? And there are two possible ways. One possible way is you enumerate all possible scenarios, right. So, you say C1 is when John is not listening to music, C2 is when John has not gone on an errand, C3 is when he has not had a tiff with Julia, etc., etc. And then you say that if a burglary has happened and C1 has happened and C2 has happened and C3 has happened and so on, then he is going to call. Now, you can already see what is the problem with this. What is the problem with this? Too many possibilities, and we cannot enumerate all of them, right. This is called the qualification problem. One such example of the qualification problem is, my car doesn't start, what is going on? And you see that your car doesn't start, you have checked the engine, you have checked the battery, you have checked, you know, various wires that are going in and out, and you finally have no idea, and finally you realize that the potato was stuck in the tailpipe. Now, any car diagnosis system is not going to model the fact that there is a potato in the tailpipe. So, this beautiful example is called the potato in the tailpipe problem, or also called the qualification and the ramification problem. The qualification problem is that one particular event may have many causes, it is impossible to enumerate all of them. Ramification problem is that one particular event has many effects and it is not possible to enumerate all of them. So, this qualification and ramification problems make this an infeasible enterprise. So, what is the alternative? Well, the alternative is that you say, John may be out, there may have been a tiff, he may have been listening to loud music, he may be drunk. Let us all put it into one scenario where he does not call, and let us say in practice, how often would that happen? That would, let us say, happen 15% of the time. So, we can simply say that in 85% of the worlds, when there is alarm, John is going to make a call. And in 15% of the worlds, irrespective of the reason why he did not make a call, he would not make a call. Right? We just don't worry about enumerating the reasons. Yes.
But I understand that when you are criticizing a model which gives both emphasis on detail and logic, and you are saying that a model which has currently less information and is predicting results most of the time is good. But in sequence of time when we have more precise information, more precise things, then probabilistic models will be so not good.
So, Parth makes a very interesting observation. He says, I have been criticizing the model that requires you to put in more information, that is more detail oriented, whereas I am saying that the better model is the one which has no detail or relatively less detail and has just put it into the probability. So, shouldn't the model which is more detail oriented and more fine grained be a better model? And what is our answer to that? Well, let us not worry about efficiency. Look, all models are wrong. The question is which one is more useful, right? Now, can you enumerate all such possibilities? You may or may not be able to. Can you even observe all the possibilities? You may or may not be able to. So, if you do not know whether John has gone off on an errand, if you do not know whether John has been hearing to loud music or not, it is very hard for you to make inferences about whether John has called or not, or whether John is going to call. There may be alternative reasons why John can call. He may just call to trouble you. He knows that you are having a party, he is stuck at house living alone, he is just calling you to trouble you so that you come back, and then he can say, oh, I thought the alarm went off. Anything can happen. Now, you do not know whether that is what is going on in his mind or not. You can't observe all such things. And if you can't observe all such things, the best you can do in this scenario is to make a likelihood judgment, to make an observational, based on the observation, get a sense of what do I believe in at this point in time, right. Again, the short answer to your question would be that if you can put in the details, if you can observe the details, then you can always put it in the probabilistic model, that will give you more power. But of course, if you start putting in all the details in the probabilistic model, then you can also have to start asking questions, okay, what is the probability he is going to call if he is drunk but he has not had a tiff? What about if he is not drunk but he has had a tiff and he is listening to loud music? So, to enumerate all such possibilities, and that will make it harder for you to model it effectively. So, there are challenges in any side. Always the question you have to ask is, given the current situation, how much do I model, how much do I not model, and what am I not modeling, how do I capture the existence of that or the possibilities of that, and the probabilistic model gives us a good framework for it. Now, with this background, I think many of you would agree that probabilistic models are important, and what is the equivalent language from logic into probability world, and one of that languages is the language of Bayesian networks. So, last class we talked about simple inferences, independence, conditional independence, Bayes theorem, but now we are going to use all those ideas into one graph, a graph structure which represents the problem. And this graph structure and many other similar graph structures collectively are called probabilistic graphical models. You would hear the term PGMs mentioned by a lot of the AI researchers even today, but definitely 5 years ago. So, probabilistic graphical models were the rage in 2000s, early 2010s, late 90s. There was a huge amount of work that was being done in probabilistic graphical models. Many different kind of models have come out: Bayesian network, dynamic Bayesian network, Markov network, conditional random fields, etc., etc. Right. So, the next thing you may remember is that we said that for any n random variables, if I give you the joint distribution, I can compute every query. We said this, but we said that the joint distribution is not possible to enumerate. So, in general, what we need is the joint distribution, and in general the joint distribution P will require exponential space. However, by using Bayesian networks, we are going to make it compact. That is our goal. So, we will give you a factorization of joint probability distribution that allows us to store it with very limited number of parameters. Okay? So, Bayesian networks provide a graphical representation Oh, and what is the fundamental basis on which these graph would be arranged? That would be conditional independence, and all of this will become clearer in the next 10 minutes for you. So it would be usually compact. They would require assessment of far fewer parameters than a full exponential one, and inference may or may not be efficient. Sometimes it will be efficient, sometimes it will not be. So we discussed last time that if you are at the dentist and if you have to somehow manage to place all these variables into some kind of graph structure, it would be what? So it would be that weather is completely independent of cavity, toothache and catch. So there will be no edge between weather and them. On the other hand, cavity would be the one cause for multiple effects. The effects would be toothache and catch. So there would be edge from cavity to toothache, there would be edge from cavity to catch, but there will be no edge from toothache to catch, because toothache does not directly influence catch or vice versa. After 2 classes, you would be able to read off this graph and say toothache and catch are conditionally independent of each other given cavity. In fact, this graph structure says this in so many words. So we also have to learn how to read such graph structures, okay? But first let us talk about syntax. So the syntax is a set of nodes, one per random variable, right? Here there were 4 nodes, one per random variable. It will be a directed acyclic graph. Notice that this was directed and it is acyclic, and what is the notion of a link is sort of somewhat fuzzy, but for now just imagine a link means it directly influences, okay. So x1 to x2 there is a link, that means x1 somehow directly influences x2. So like weather does not influence anything, any of these 3, cavity influences toothache. Moreover, we have to somehow talk about the probabilities, right? We have not been talking about probabilities. So additionally, with each node, I am going to associate a conditional probability table, okay? And this conditional probability table would be a distribution for each node given its parents. So probability of xi given all the parents of xi. So if you are discrete variables, now people have studied continuous variables also. We will in this class not talk about continuous variables, but there are ways to say what if the child is continuous, the parent is discrete, what if the parent is continuous, child is continuous, what if the parent is continuous, child is discrete. People have thought about functions for that, functional forms, and the book talks about it. So you should read that. But for now, we will just worry about discrete variables. So we will say that for discrete variables, the conditional probability table is a distribution over xi for each combination of parent values, okay. This is what we had discussed, how many parameters we need. So before we go there, we are now in this burglars and earthquake world. We have burglary, earthquake, alarm, John call and Mary call. Now if I had to ask you to tell me what should be the graph structure, just intuitively, even though you do not quite understand what does the graph mean really, what would you say? Who would be the parent of what? What directly influences what? Earthquake influences alarm. Earthquake influences alarm. What else? Burglary also influences alarm. In fact, alarm can go off because of 2 specific reasons, right? What else? Alarm influences John call. Look, John does not care for burglary directly. He only listens to the alarm. If alarm goes off, he may call. On the other hand, for Mary, same thing, only alarm influences Mary. So if I simply asked you to make a graph structure, you would have made this graph structure, right? And that exactly is the graph structure for this Bayesian network, the most compact graph structure. Now I should not say that is the graph structure, because if you do it in some different order, you can come up with a different graph, okay. Now that is a little complicated, but to think about. It is very complicated to think about how to do this in a different order, but machines have a problem with this. So in practice what happens is the human gives the graph structure. The human says, look, I will give you the graph structure, you figure out the probability. The human can't say that should the probability be 0.9 or 0.91 or 0.902. Humans are not very good at this. Humans are qualitative people. You can't say that 100 rupees is okay for me, 101 is really expensive. You can't say that, right? You can't say that this is my cutoff. Have you seen these eBay auctions? You have to say what is the maximum you are allowed to pay, you want to pay. Like how can you give a maximum? For you 10,000 rupees and 10,001 rupees is very similar. So, it is very hard for us to draw a line, it is very hard for us to give thresholds. But we can sort of give ballparks, we can say this is expensive, this is too cheap, etc., etc. So, humans will be really good at giving the best graph structure many times, but machines are better with computing probabilities. And this is how our typical division of labor happens, although there are methods for doing what is called structure learning, which basically means learn the graph structure also.